I welcome you all in my new video and just giving you a recap what we were learning. We saw the main problem of vanishing gradient problem in training of deep language models. Researchers was facing this problem for a long time, and after that we saw fixes that using better optimizers, better activation functions, and doing some tweaks in transformer architectures, we were able to train deep language models. And now our learning in early layers are happening right now. So this was a good news. This is a good news for now. And they thought that okay, now the roadmap is simple. That why don't we give more and more data to these deep models and get better results and better AI, making better AI. So there is nothing wrong in this idea. Okay, so today's topic is about scaling laws of LLMs. OpenAI gave the research paper in 2020 about these scaling laws. At the end of this video, we will understand that why these scaling laws came into picture and what OpenAI said in that research paper. So let me take you to my presentation. This time I came up with better visuals and diagrams so that you can understand simply that what is the concept. So this is a better way to understand something, to learn something. So let's quickly start our today's topic. And yes, on top of the screen, you can see what was the idea, that more data, more high quality data, that gives the model more knowledge to learn from. And more bigger models, what do I mean by bigger model? That there are many number of huge number of parameters. For example, we saw weights and biases. So we are saying parameters to these weights and biases. And when we have so many of these parameters, then we have bigger model, and it has more capacity to learn complex patterns and relationships. And by combining more data and bigger model, we are going to get better result. This was the idea, and there is nothing wrong in this idea, because previously we saw in machine learning models and deep neural networks, by giving more and more data, our model was giving better results with better accuracy. The model understand better, make fewer mistakes, and gives better results. But this graph shows you that x-axis shows the more data and y-axis is the performance. As we increase the data, the performance increase rapidly in start, but it slows down at this point. And then after that, it is going it will be stagnant after a certain point of time, and it is not improving. So this was the problem. This was the next second big problem that researchers faced around 2018, 19, and 20. And they saw that it is not like giving more and more data and we can get a better model, we can get better AI. What was happening? In right, there is a larger model, and in left, there is a small model. So you can see in small model, there are less number of parameters, means less number of weights and biases. So the small model has less capacity. It has limited understanding. It has fewer connections and cannot learn complex patterns. So the output also not reliable in case of small model. But in case of large model, there is very high capacity, very much better understanding. It has more connections and can learn complex patterns, and its output also better. But in small model, you can see that by giving huge amount of data to small model also not work. But in case of large model, giving less data to this large model also not works. So both the things are vice versa. So in this example, you can see giving a small child 100 advanced books. More books do not help if the reader is not ready. Yes, you cannot expect from the fifth standard child that you can learn machine learning, real analysis, linear algebra, because the child is not ready yet. It takes time to process the advanced concepts, to understand the foundations, that That is what we are doing right now to understand LLMs and Gen AI more better. We are building our foundations. So that is what a child is doing in first 10 to 15 years in school and college. So yeah, so let's come to the point that small model has limited capacity and we cannot give huge amount of massive amount of data. If we combine both, then we will get waste. It is like we will not get better results by doing so. So in 2019 and 20, OpenAI researchers at OpenAI and other community also, they all realized that we should increase all the three components simultaneously in parallel. So what do I mean by this statement? That in this picture you can see model should large enough to get to learn complex patterns from the data, and data also should be that amount that model can get relationship, model can understand the data, model can extract the complex patterns. So data is also, we should have enough data. And the third thing is compute. We also have enough amount of compute to process, to train the model on huge amount of data. So all three things grew together. If any one thing is less, then we cannot able, then we could not able to train deep language models, and hence we cannot get the power of AI. So so first understand what is compute, and before that, to train these language models, to train language models, you can in training, we saw in transformer architecture, when I was explaining you the transformer architecture, everything during training, everything runs in parallel. There are lots of multiplications and addition of big matrices happen there, and everything runs in parallel during training. Inference time, there was a sequential output we were getting, but during training, and the most of the time researchers invest in training these deep language models. So to train these deep language models, we need GPUs, because CPUs, because first understand what is GPU. So GPU is basically graphic processing unit. It is a specialized processor designed to do many calculations in parallel. This is the beautiful part of the GPU, that it can do multiple mathematical operations in parallel. And how the GPU can do this thing? Due to the cores. Thousands of cores optimized for parallel tasks. But oppositely, in CPU, there are few cores optimized for sequential tasks. What do I mean by sequential task? That one first mathematical operation can be done first. Once it completes, then the second. Once the second completes, then the third. So this is sequential learning, sequential processing. But in GPU, there is parallel processing. Multiple mathematical operations are happening parallelly due to these cores. Okay, and what is core? Core is a tiny processing unit inside a GPU, and each core can perform math operation independently. So you can see in the screen, thousands of core work at the same time. Each core handle multiple operations every clock cycle, and more cores, more parallel work, high performance. Now, the most important thing here, how do we measure the compute? So compute is measured. What is the unit of compute actually? We should say, what is the unit of compute? The unit of compute is flops. You might be hearing this unit for the first time, but don't worry, it is just a unit. For example, we can measure distance in kilometers or miles. Similarly, we can denote compute in flop units. So flop is floating point operations per second. It measures how many math operations a GPU can do in 1 second. So examples of operations, you can see addition, subtraction, multiplication, and division. So these are the mathematical operations. So if a GPU has X flops, what does it mean? It means it can do X operations every second. So every one GPU has X flops. I will tell you what are the number of flops a short time. So be with me. So we understand what is compute. Compute is flops per second, and how do GPU does work high level. So we saw in transformer architecture we give input data tokens, and every tokens are we give a large amount of tokens, and every token processed parallelly, and output predictions also happen parallelly. So GPU can do, because of many cores present in GPU, thousands of cores process data simultaneously. So each token, there are many multiplicative operations, bigger matrices multiplied together, and after that we get the output token. Okay, so tokens go through the model, matrix multiplication, addition, activation functions also, and millions and billions of operations are performed. So more token, more parameters, more compute. Okay, and why GPU is better? Because massive parallelism, high throughput, efficiency, high memory bandwidth. So these are the concepts we need to understand about the GPU, and this we already got to know that what is compute, that is total number of math operations done during training. And yes, this is the main equation that OpenAI in research paper, this is the important equation they give. When researchers train deep language models, first, what is the thing they can consider, they can be most careful with? The thing is, what is our compute size? Because training deep language models with so many parameters and very huge amount of data is not possible on on simple laptops. We need multiple GPUs, bigger systems to handle. And the first thing they need to understand, what is our compute size? What is our compute size? How many GPUs we have? So that is how we first understand that to train this language model with this much of data, we need this much of compute. So compute is fixed basically. Compute is fixed, and then we break the n and d. The next task is to find what is the right number of n and d. And what is n is basically model size, number of parameters, and d is amount of data, number of tokens. Okay, so model size into amount of data is equal to total compute. This is the simple equation that they gave in that research paper. And I said that compute is mostly fixed, that we have this much of compute, and compute is what? Flops per seconds. Okay. And after that, our main focus will be to get right number of n and d, right value of n and d. But this is not, there is not a straightforward formula to get n and d. So, let me give you an example. When we have fixed resource, for example, if we have one GPU and fixed time, so the total work you can do is limited. Okay, so suppose a GPU can do 1 billion unit of work mostly. Okay, so unit of work means 1 billion mathematical operations per second. If we have one GPU, now we must choose n and d such that n into d is equal to 1 billion. As I said, there is no straightforward answer to calculate to get the n and d value, but we can run experiments. So for example, we take three options. We have three options. Okay. First option, we can take n is equal to 100 million and d is equal to 10 million. So by multiplying 100 million into 10 million, we will get 1 billion. So this is one type of model we can consider. The second one is n is 10 million and d is 100 million. So this is also 10 into 100, 1 billion flops per second. Option C, what we have, n is 30 million, d is 33 million. So by multiplying 30 into 33 is approximately 1 billion. So our compute is fixed 1 billion. We have three options. So I want you to think about that which option we will choose, which is the best option for us to train the language model, to train the deep language models. Because in option A, we have so many parameters, because n value is very high, 100 million parameters, but we have 10 million tokens, that is too less. In option B, we have very less number of parameters, 10 million, but we have 100 millions of data tokens. And token is nothing but a piece of word or a word. Okay, so I already explained you what is token. Token is just a word. Okay, we are training, we are giving text data. We are giving text data to these language models, and first we break text into tokens, and token is nothing but a word or piece of word. That's it. Okay, so don't confuse with token term. So I hope you all agree that option C is very much reliable. Option C is very much better than option A and B. In option A, our model will overfit. It memorizes the small amount of data, and it will perform very poor when unseen data gave to this model. In option B, there is a case of underfitting. It means our model performed very poor during the training and as well as during the testing. And in option C, it might be a case that we will get better results because everything is balanced. We have fixed compute size, we have balanced N and D value. Means we have balanced number of parameters as well as data tokens. So all three options we just choose. So I already explained you the case 1, case 2, case 3. So we will go with the balanced approach, that is case 3, because capacity matches data, enough information and enough capacity to learn. And we will observe that during training, steady improvement. This is basically loss. So loss goes down gradually and it becomes very less during the training, and validation loss also. But in case 1, there is a case of overfitting. Overfitting means when we train our model, it memorizes the data, it memorizes the patterns, and when we give unseen data, new data to our model to predict something, then it returns very poor results. So validation loss will be very high. But in case 2, we have very small model and data too large. So this is underfitting. Means that our model is not able to capture too much information, is have very less capacity, and it cannot able to understand too much information. Model cannot store all patterns. So loss decrease slowly and early. So loss is high in this case during training as well as testing. So simple intuition, use brain plus no books waste, many books plus small brain waste, and balanced approach, we will get better result. So scaling loss shows that increasing N, D or C reduce loss, but C is limited in reality. So we must choose how much model parameters as well as data tokens to use. And there is no straightforward answers. We have to run experiments, whatever with the value of N and D suits us, then we choose that value. Okay, so balanced approach always gives the best. Now let me show you what are the GPUs available in the market and what are their, flops. Flops, as you know, floating operations per second. Compute is measured using this unit. So on top of it, we have H100 NVIDIA, and these all are very, very expensive GPUs from NVIDIA, and they have enormous amount of compute power. So, so the important things to note down here: FP32 and FP16. So first, let me tell you that FP32 is nothing but it is showing that 51 trillion flops. T stands for trillion. That NVIDIA H100 SXM can do 51 trillion floating operations or 51 trillion mathematical operations per second with high accuracy. but it takes more time. In FP32, in FP16, the same GPU can compute, can do more mathematical operations, but with less time and less accuracy. So FP16 is basically fast than compared to FP32. This is the basic difference in FP32 and FP16. And all the five GPUs are very expensive. They used in industries and primary use large language model training, LLMs, AI training, next gen LLM training. So this is the use case of these GPUs, and any normal person cannot able to buy these expensive GPUs. So for consumer use, NVIDIA gave other options, for example, RTX 4090, 4080. So these GPUs we can buy from the market, and these are also very, very fast, 82.6 trillion mathematical operations per second in FP32. And similarly, you can see how fast they can, and they also typically use very high power. They eat big electricity, and the bill of the electricity is very, very huge to train these large language models. And to train LLMs, industries have to spend days, weeks, or months to train these models, and enormous amount of money spend it to train these AI models, and that is how. So GPU mostly comes in variants. The first five GPUs are for the industry purposes, and the next four GPUs are from consumer side workstations we can buy from the Amazon or other marketplace to use these AI, use these GPUs. And alternatively, we can rent GPU power from the cloud services, for example, AWS, Google Cloud, Microsoft, and other GPU providers also there in the market on the internet. So you can search about them. So now, as we are ending our this video, I want you to give you a glance that how much compute is used to train the famous frontier models, famous LLMs. So GPU one have trained on less than 100 GPUs, and all are from NVIDIA. GPU one, very few GPUs as compared to other GPT versions. GPT-2 estimated 100 to used 100 to 500 GPU. GPU-3, GPT-3 trained on 1K to 10K GPUs. You can now have an idea that how many GPUs they use to train GPT-3 model, and GPT-4 even more, 10K to 25 GPUs, and these GPUs eat enormous amount of electricities. And GPT OpenAI spent billions of dollars to train the GPT models till now. And also Google also used multiple TPUs. So TPU is basically another form of GPU. TPU is tensor processing unit, and it is nothing but TPUs are specifically made to process the tensors. Tensor means matrices, mathematical operations, but it is not like the TPU are more better than the GPUs. It is nothing like that. TPU are made by the Google, so they use TPU to train their models. So Gemini use 10K plus TPUs, and now famous Meta, Facebook, Llama A100, 2K to 8K GPUs used to train the Llama model. And Llama, all these models in future, we are going to, we are going to use these models in practical when we will be doing code. So first we have to understand which model from which company and what is the compute power. So Llama comes in various variants. So their main bigger model trained on these number of GPUs. So these are estimated numbers, and these are almost correct. So similarly, Claude also thousands of GPUs, H100 very expensive. Grok from Elon Musk, H100 10K plus GPUs, and DeepSeek also 10K plus GPUs. And all these models are very big, except GPT 1, 2, 3, small. These are considered to be small model, but after that, all the models are very large models because they trained on very huge amount of data. That's why these language models can be considered as large language. This was all about scaling laws that researchers gave around 2020s, that to train deep language models, we need to increase all three things simultaneously in parallel. What are the three things? Compute, data tokens, and model parameters. So that is it for today. I hope you enjoyed this video. As I said in the start of my video, we are almost completing our foundations to understand LLMs. It will be a super exciting journey with you all. I hope you like this video, and I request you to please like, share, and subscribe to my channel so that you can see my latest videos. And thank you so much for watching my video.